Hey there, AP scholars. Section 2.6 is about resonance and formal charge. We talked a bit about the idea of formal charge already, so there's really not much new there. And resonance kind of hinted about already as well. So let's just dive into it and make this a quick one. So when we look at a diagram like this, okay, a Lewis structure for the chlorate ion, we see that one oxygen is behaving differently than the others. Yes, we know it's an ion, so there's an extra electron, but why does this one get it? Why doesn't this one and this one? It doesn't make a difference. Well, I mean, I don't know, maybe if you're triplets, it matters to you who gets which thing, but, the thing is with oxygens, they're all equal. Neither one has a stronger electronegativity than the others, and that's where resonance comes into play. Because they're all equally strong, when that extra electron comes into play, they're all pulling on it. And remember that electrons are always in motion. So it's not like, all right, once it's here, it's here. The other oxygens are not really all that far away. So as this electron starts rounding here, it could get sucked into here. And now all of a sudden this one's -1 and then this one's -1. And the same thing then with the double bonds. The extra electron, if the extra electron comes onto here, then the extra bond is going to be pulled over towards that way. So everything is in flux. So the double bonds are sometimes here, sometimes here, sometimes here. So we're going to treat it as if they're all equal, and that is what resonance is about. So here are three resonance structures for that chlorate ion that I was just talking about. Yes, there should be brackets around it, and I wouldn't have drawn it this way, but it was the best image I could find since I'm not the neatest of artists. Anyway, when we see that there are multiple valid structures, okay, we talk about resonance structures. So you notice here that we have the single bond on the right, here the single bonds in the middle, here the single bonds on the left. And I know you could argue that if I just turn the molecule, wouldn't that be the same thing? Yes, but let's pretend that, oxygen 1, oxygen 2, and oxygen 3 maybe are slightly different isotopes of one another because they have different numbers of neutrons. Then you'd be able to tell the difference there. That's a rare thing, but that's why we talk about this. So we're assuming that all the bonds are equal. It's not 2 double bonds and a single bond. It's really 5 bonds being shared by 3 atoms. And so we talk about it in terms of the fact that each oxygen would have 5/3 or 1 2/3 bonds. We mentioned bond order before and said a single bond is a bond order of 1, a double bond is a bond order of 2, triple bond would be bond order of 3. Well, when we get into resonance, then we start getting into fractions for bond order. So for example, in this case, since there are 4 bonds being shared by 3 oxygens, we would say that the bond order of this is 4/3. Each oxygen is 4/3. So there is no 2, there is no 1. They're all 4/3 because they're all equal. Now, how that played into the geometry thing we kind of talked about with formal charge and the fact that in many cases when we go to a lower formal charge, you notice that we would eliminate the idea of resonance, where this one would have to show resonance to make all the bonds equal. In this case, we see that all the bonds would be equal, and bond order of 2, where here they're all bond order of 4/3. But the point is that, again, they're all equal, so these should also be equal. Even if, whether we regard the bond order as 2 or 4/3, we should consider that in any case, the bonds should all be equal between sulfur and any of the oxygens. Really, that's it. That's all that you need to know for this section. Like I said, not much new there. So go bang out the AP assignment, and you are good to go.